All right, so now that we've kind of torn down the foundations of VSEPR, there's one other part that we have to attack from your general chemistry teachings, okay? And that has to do with hybrid orbitals and the symmetry of orbitals and their relation to VSEPR. So here's the problem, okay? Orbitals don't have, a lot of times, the correct symmetry for bonding. Atomic orbitals don't. And there's a fundamental principle. You can prove this through a variety of mathematical ways, that atomic orbitals must be of the same symmetry to one another in order to form a bond, okay? In order to form bonding orbitals. And so Linus Pauling, great Linus Pauling, knew this problem for a long time. And what he did was he bridged, his goal was to bridge VSEPR geometries, which were known, with these principles of quantum mechanics, right? Where from the math that atomic orbitals have to have the same symmetry. And so this is the problem, just in one example, right? Take methane, simplest organic molecule. We know the symmetry, it's TD here. Later we'll learn that TD just is shorthand for tetrahedral symmetry. Okay, so it's a tetrahedral symmetry. That's what VSEPR predicts. We know why. It has 4 ligands, right, and no lone pairs. So steric number 4, which is tetrahedral. 109.5, all the bond angles are the same. 109.5. Okay, very symmetric molecule. Here's the problem. What orbitals do you have to make bonds? Well, on hydrogen, all you have is 1s. There's only one valence electron on hydrogen, and it's in the 1s. So all these hydrogens just have a 1s orbital. So you have 4 1s orbitals each, okay? And the symmetries of that are what's called A1 symmetry in the TD space. We'll get into this in chapter 4, but just believe me at this point that the atomic orbitals have what's called A1 symmetry, and the p orbitals, okay, what's on the carbon? Carbon has 3 p orbitals, right? Px, py, pz, and an s orbital. And the p orbitals have a different type of symmetry. They have what's called T2 symmetry, okay? And so fundamentally, mathematically, you cannot combine in methane, in tetrahedral methane, you cannot combine a p orbital of T2 symmetry with a different orbital of A1 symmetry, okay? You can combine the s orbital, 2s orbital of carbon, right? The 4th atomic orbital on carbon does have the right symmetry, so that can bond. But you can only make one bond, okay? And the p orbitals are just left out, mathematically impossible for them to make a bond. Linus Pauling knew this was a huge problem, right? A huge problem with Lewis structures, which he was a big proponent of, and of VSEPR. So what did he do? He invented the idea of hybrid orbitals to fix this problem. It's just like he invented something new just to get everything to fit right. Okay, that's the only reason why hybrid orbitals exist, or the idea of hybrid orbitals exists. I'm arguing that hybrid orbitals do not actually exist. It's a theory, just like anything else is a theory, but they're a very poor reflection of reality. Okay, and so what he said is, hey, I'm going to take that 1s orbital, I'm going to take those 3 p orbitals on carbon, I'm going to mix them together and make a new type of orbital. I'm calling sp3 orbitals because it's 1s and 3 p's together. And those are going to have the right symmetry, this TD type symmetry, to bond with hydrogen. They're actually going to have A1 symmetry, the same symmetry as the s orbitals do on hydrogen. So again, it's just a total invention, a total way of trying to fix a big problem in chemistry at the time. And you guys probably have heard of sp2 hybrid orbitals and sp hybrid orbitals. These help explain how you can get trivial planar geometries and linear geometries. But all this does is make us feel better about VSEPR, because now we can use have the correct symmetries. But again, I really stress they're complete inventions. It's a complete myth of hybrid orbitals. How do we know for sure hybrid orbitals aren't true? Turns out the electronic structures predicted by hybrid orbitals usually don't match experiments. And so, in this picture here, you have bonding. Sure, you have 4 single bonds, and they're mediated by identical orbitals. And that says that you should have the energy levels of these 4 orbitals should all be equal. And there are ways of showing that that is not true experimentally. And if you actually do the molecular orbital diagram, which we will talk about this in a little more detail later when we get into MO diagrams, don't worry about the derivation of this. But I'm telling you, this is what MO theory says, which is a better reflection of reality as compared to VSEPR for methane. You actually have, okay, you have 8 valence electrons, 8 valence electrons forming 4 bonds still, 4 single bonds. All single bonds are equivalent still, but you have these more delocalized structures. And importantly, very interestingly, there are 2 different energy states. 6 of the electrons are at a higher energy level, and 2 of the electrons are at a different energy level. These all contribute to the 4 single bonds. And each of them have sort of 3/4 T2 character and 1/4 A1 character. Again, the details here aren't important, but I don't want you to walk away from this thinking, oh my gosh, methane has 2 different types of bonds. No, it doesn't have 2 different types of bonds. All 4 bonds are equivalent, but the 8 electrons that stitch those bonds together, stitch those 4 bonds together, are contained in 2 different groups, 6 of them in one group, 2 of them in another group. And as such, they have 2 different energies, the molecular orbitals do. And you can actually use something called photoelectron spectroscopy to prove, basically totally disprove the idea of hybrid orbitals. And so, I'm sorry, in general chemistry, we taught you, I don't really teach them because I don't like them to teach things that I think are poor reflections of reality. But in general chemistry, a lot of people taught you about hybrid orbitals. I'm sorry, okay? But yeah, they're not true. So you can do the photoelectron spectroscopy, shine a certain wavelength of light, ultraviolet light, and you actually can see there's 2 peaks, and they're in a 3-to-1 ratio because it's there's 8 electrons total, a 6-to-2 ratio, and this matches exactly what a molecular orbital theory would predict. And so, don't worry too much about a lot of the symmetries and the numbers that I've gone over in this part of the video. I just want you to appreciate, really fundamentally, VSEPR is all an empirical theory. It's a rationalization, and that spills over into problems that you can have with Lewis structures, problems that you can have with hybrid orbital theories not being correct, right? And that a better reflection of reality of how bonding works is found through the principle of quantum mechanics, right? Which manifests itself, as we will see, in a theory called molecular orbital